Welcome everybody to lesson 10 of our friendly introduction to abstract algebra. Today's video we are taking a look at matrix groups. In the last video we took a closer look at the dihedral group as a subgroup of the symmetric group of degree n, and in this approach we didn't need matrices. In discussing matrix groups, of course, we need knowledge about matrices. So again, if you've never heard of matrices or have no background in linear algebra, maybe you want to skip this week's lesson, which again is not going to be much of a problem, but you're going to miss a very important non-abelian group of order 8. So maybe just take a look at the end of the video so that you have heard about the so-called quaternion group. All right, let's get into it. We assume that F is a field. And then we take all the n by n matrices with entries in this field that are invertible, which means exactly that their determinant does not vanish. And the set of these matrices is called GL sub n of F. And we will show that it is a group, of course, together with matrix multiplication, and it is called the general linear group. Hence the abbreviation GL for general linear. And here I could say if with 2f, if and only if n is greater than or equal to 2, this group is non-abelian. I'm always not sure about the correct spelling, maybe with hyphenation, non-abelian, whatever, you get the idea. That looks strange. So maybe this is better, non-abelian. And it is an infinite group if the field itself has infinitely many elements. So for example, GLN of Q, the rational numbers, or GLNR, the real numbers, or GLNC, all those are infinite groups. On problem set 10 there will be an exercise that studies this here for finite fields. If you have never heard of finite fields before, do not worry. When we are studying field theory, we are going to discuss those thoroughly, and this here is not really important for the course of our introduction to group theory. All right, let's take a look at the proof. First of all, we have to show that matrix multiplication is indeed an inner operation, meaning that if I take two matrices of this set here, then their product is again an element of this set. For this I abbreviate this here with G. But if you have ever heard about determinants, then you know that if A and B are invertible, then so is their product because of the determinant multiplication theorem, or whatever it is called in English. The determinant of A times B is the determinant of A times the determinant of B. So this is simply a product in the field. And of course, if those are not zero, then the product is not zero because we have no zero divisors in any field. So and this exactly means that A times B again is invertible, and by definition then it lies in GL and F. So we have a set together with an operation, and the set is closed under this operation. Now it's a well-known fact that matrix multiplication is associative, and it really is a nightmare to write that down explicitly if you don't know about linear maps and have to do it on the matrix level, but we just assume that this is known. So our operation is associative. Clearly there's an identity, namely the identity matrix, which has ones on the diagonal and everything else, all the other entries are zero. This is the neutral element with respect to matrix multiplication, and the existence of inverses is guaranteed by definition because we are looking at all the invertible matrices. So A inverse, the inverse matrix is the inverse in this group. To calculate this inverse explicitly, you could, for example, use Cramer's rule, but this is not what this is about. We simply want to convince ourselves that it is a group, and this shows all the group axioms are satisfied, so GL and F is a group. Now, this statement here, if n is 1, then what is GL1F? those are all the 1 by 1 matrices, so simply all those numbers written in brackets. So I could as well leave the parentheses away, and those are simply all the field elements, and the determinant is the number itself. So this simply means that the element of the field is not a 0, so we take f star, which means exactly f without 0, and this of course is abelian. Now if n is 2, we take these two matrices here, and they exist in any field, because any field has the elements 0 and 1. And now here's a quick reminder about matrix multiplication. To multiply these matrices in this order, you take here the first column of the second matrix, you rotate it by 90 degrees, and you put it in your mind above this first row here, and then you multiply. 1 times 1 is 1 in any field, plus 1 times 1 is 2. Then for this entry you do the same with the second row here. 1 times 0 is 0, plus 1 times 1 is 1. And then for these entries here you take the second column, put it above here, and then you multiply. 0 times 1 plus 1 times 1 is 1. And 0 times 1 times this here, 0 times 0, 1 times 1 gives me again 1. Now, if the characteristic of the field is 2, then this here is 0. 2 is the same as 0, as crazy as this may sound. But there are fields with characteristic 2, but still this matrix is different from this matrix, independent of whether 2 is 0 or not. Now if I change the places of a and b and calculate b times a, please do that yourself if this is new to you, the rule I just explained, you will end up with this matrix. And those are clearly different. Even if 2 is 0, they are still different. So this shows that for n equals 2, GL2F is a non-commutative group. And for n greater than or equal to 3, simply take these two matrices, write them here as 2 by 2 blocks, and then fill in the rest with 1s along the diagonal and 0s elsewhere, and the same for the matrix Bn. And then essentially the product boils down to this here in those boxes. And this shows that GLNF for n greater than or equal to 2 is always a non-commutative group. Now for the last statement about the order of this group, the set S for scalars consisting of all the multiples of the identity matrix. So put lambdas on the diagonal, and lambda runs through all the elements of the field except for 0, is clearly a subset of GLNF. Why? Because the determinant of such a matrix is lambda times lambda times lambda and so on, so lambda to the power of n. And if lambda is not 0, then the determinant is not 0. So, and clearly this set has the same order as f star. I simply take all the non-zero field elements and put them on the diagonal. So if this here is infinite, then this here is infinite, and this means that GLNF itself must be an infinite group. That's it. All right, and now we have a completely new example for a possibly infinite non-commutative group, namely GLNF n not 1. All right, some more examples of subgroups of these general linear groups. If I take SO2, those are all the orthogonal matrices in R2 with determinant 1. This here, the S stands for special orthogonal group. Those are all the rotation matrices. And you can show that they have all this form here. In the first row you have cosine theta, sine theta, and in the second, did I say row or column? I always interchange. I always mix up rows and columns, I'm sorry. So in the first column you you have cosine theta, sine theta, and in the second column you have minus sine theta, cosine theta. Theta can be any real number, can even be 0, because then you have here 1, 1 and 0, 0, so you have the identity matrix, which is clear if you rotate by 0 degrees, this is clearly the identity. And this here is easily to be seen a subgroup of GL2R. Okay, details are left maybe for the exercises, or if you know about this stuff, then it's obvious. Now in complex notation, this here becomes e to the theta I, because by the fundamental Euler identity, e to the theta I is nothing but cosine theta plus I sine theta. So we can write these matrices here in a compact form if you want to use complex numbers like that. And this is called U1, the unitary group. Those are all the points in the complex plane that lie on the unit circle. And this here is clearly a subgroup of GL1C, which is nothing but C star. So the complex numbers without 0. If this is all overwhelming to you because you don't know much about matrices or complex numbers, do not worry. Those are just some nice examples, but they will play almost no role for the rest of this group theory course. Now on problem set 3, we talked about the matrix representation of the dihedral group. And this is clearly a subgroup of GL2R because symmetries of an n-gon are invertible matrices in matrix form. So for example, D4 in matrix form is a non-abelian, maybe again the hyphenation, subgroup of this group of order 8. So this gives me a concrete realization of a finite matrix group, in this case of order 8, which is non-abelian. And there actually is another non-abelian group of order 8 that is not the same, or later we will say isomorphic to this group here. This is the so-called quaternion group. Now, if you're familiar with Hamilton's quaternions, then this will make a lot of sense to you. If not, do not worry. Simply accept that we take these 4 matrices here. In this case, we write for the identity matrix E instead of I, because the matrix capital I is this matrix here, with the imaginary unit I and minus I on the diagonal. J is this matrix here, and K this matrix, where the i's are on the other diagonal. Now if I take these matrices and their negative matrices, I have clearly a set of 8 matrices, complex matrices, and on the problem set you are supposed to show that they actually are a group, and therefore a subgroup of GL2C. And this is always a nice example when we talk about groups of order 8, because here we have 2 different groups of order 8 that are non-abelian. Maybe again here. All right, that's all I have to say for this week's lesson. If you want to do some of the exercises, as I said in the beginning, it is not essential for the rest of the introduction to group theory to know that much about matrices, but from time to time, those here are nice examples. Next week, we are going to start talking about homomorphisms, which is essential for developing any real theory. All right, looking forward to seeing you again. Have a good one and bye-bye.